All right, this is a fun video. I really like this video because the first real example is a pretty wacky one. So y'all are in for a treat here. So let's start off by remembering one of the first graphs that we looked at. All right, one of the first graphs we looked at in this section was the function that had a hole at 2. It kind of looked like this. So in this case, the limit from the left is different from the limit from the right. Again, let's say that this is positive 2 and down here it's negative 2 right there. All right, so the limit from the left, right, as we get really close on the left, well, it's a constant function. And we know the limit of a constant function is that constant. If this is the function f of x, the limit from the left is negative 2. The limit from the right, again, constant function from the right, it's a constant function, is going to be positive 2. All right? So how do we write that? Here's the answer. And you may have seen this before as well. We say that the limit as x approaches negative 2 from the left of this function is negative 2. So again, as a side note, this right here means from the left. It's like, it looks like an exponent. It's a superscript. It's a superscript negative, and it means from the left. And where that comes from, right, is if we're looking at 0, the negatives are to the left of 0. That's how you can kind of remember. Negatives are on the left, on the number line. All right, and we would also say the limit as x approaches negative 2. Oh dear. Hold on. The limit as x approaches positive 2. Woo! Hopefully you were screaming in your chair when that one happened. All right, this is the line x equals positive 2. The limit as x goes to positive 2 from the right of this function is positive 2. And again, this just means from the right. And that's what one-sided limits are about. So let's kind of combine one-sided limits and see some situations where the limit doesn't exist. Because, I was going to mention this earlier, but I'm going to mention it now instead. The limit as x approaches some number, it exists, right? This exists if and only if the limit as x approaches a from the left equals the limit as x approaches a from the right. That's L. All right, so this is a property that we're going to be using. So what does this mean? There's a lot of math here. What does this mean? This means that the limit exists only if and only if it's the same from the left as it is from the right. Okay? Limit exists only exists if the limit's the same from the left and from the right. So in this case, right, the limit from the left is one number, the limit from the right is another number. So in this specific case, we would say this limit does not exist. The one-sided limit exists, the limit from the left exists, the limit from the right exists, but because they're different, the two-sided limit does not exist. We might say something like the limit as x approaches 2 in this case of the function. We would not use equal signs. Does not exist. In this case. All right, so let's do some examples. Example 4. Find the limit as x goes to 0 of sine of 1 over x. I really like this graph. This is a cool graph. And you could either make a table here, or you could graph it on Desmos. All right. There's not really I guess there are sort of aspects to approach it without those methods, but not methods that I want you to worry about in this class right now. So find this limit. Let's look at, oops, I just turned my E into an F when I wanted to turn this F into an E. Anyway, let's look at this function graphically. Sine of 1 over x. Let's see what happens. F of x equals sine, are you ready for this? 1 over x. So as it goes to infinity, it approaches 0. As it goes to negative infinity, it approaches 0. And in the middle, I don't know what's happening in the middle. It's hard to tell. Let's zoom in a little bit. We're looking from -5 to +5. Let's zoom in. -1 to +1. Well, I still can't tell. Let's zoom in some more. -0.1 to +0.1. I still can't tell. Let's zoom in some more. -0.001 to okay, come on. What's going on here? As we approach from the left, look, our x value is so close. Look at our y values. They're bouncing all over the place. This is crazy. As we get closer to 0, this function oscillates faster and faster and faster. Okay? That's what's happening here. As we get closer and closer to 0, the function oscillates faster and faster and faster. It's not approaching a number. It's still switching between -1 and +1. There is no limit. There's not even a one-sided limit. The limit from the left doesn't exist, and the limit from the right doesn't exist. This is a bonkers banana function. Ooh, I have a banana in the fridge I might eat after this video. Anyway, so this is a weird, wacky function. There is no limit as x approaches 0. There's plenty of other limits, but not as x approaches 0. All right. It does not exist. Function oscillates between -1 and +1. Faster and faster as x approaches 0 from either side. So your answer only has to be the top one. The reason I'm including this is an explanation for you in this video. But you don't need to include this bottom part in any work. Let's look at another one. Example 5. Let's look at another piecewise function. For f of x equals x plus 1 to the left of +2. Remember, piecewise function says, so it's going to look like this line for all the x values, for all the inputs to the left of 2. And it's going to look like this parabola for all the inputs to the right of 2 and including 2. I want you to find the following. The limit as x approaches 2 from the left of this function. Now, we don't even need to make a table for this. Well, we should. In the next section, we're going to not make a table, but we should do it in this one. We don't have all the limit laws necessary to do it more formally, but you can kind of get an idea by looking at this, an informal idea. If we're to the left of 2, that's this situation, right? This is saying everything to the left of 2 uses that first piece. So as x is approaching 2 from the left, we're going to be using this piece. And as x gets close to 2, this piece is going to get close to 3 because it's just x plus 1. So that's what we think is going to happen. Let's graph it. You may not remember how to graph piecewise functions, or you may never have known how to graph piecewise functions on Desmos. Here's how you do it. Type y equals the first piece. Oh, let's go back over here and reset our scale. Let's go from -1 to 3. We really care about x equals 2. And then y, I don't know what we care about for y. So to graph a piecewise function, graph the function part, and then in brackets on Desmos, that's where you tell it the domain. x is less than 2. And we'll want to draw an open circle since the 2 is not included. So to draw the open circle, we're going to do 2, 3. And then let me zoom out a little bit so you can see. Hold down a click, write a point, make it blue, making an open circle. And then we do the other piece. The other piece was x squared minus 4. Y equals x squared minus 4. And again, this is when x is greater than or equal to. All you have to do to type then is type greater than, and then press the equal sign on your keyboard. And we don't have to worry about a circle here. We can hold down our left click, hold down left click, and turn it blue. And if we wanted to, though, we could make a closed circle here because x equals 2 is included here. This is the point 2, 0. There should be, hold down your click, should be a blue solid point here. That's how we can graph this piecewise function. On the left, it's a line. On the right, it's a parabola, or part of a parabola. Again, if we get rid of this, you can see the whole parabola. But it's a piecewise function. It's only part of that parabola. And that's how you can graph a piecewise function with Desmos. And so what is the question asking? The question is asking about the limit at 2. When x is 2, it's asking about the limit from the left. Right? The limit as x approaches 2 from the left. Well, from the left, everything on the left of 2 is on this piece. And again, it's getting really close to that y value of positive 3. So we're going to say this limit is equal to positive 3. And we can also look at the limit as x approaches 2 from the right. Now, to the right of 2, we're on this piece, the quadratic piece. What's the function doing to the right? It's approaching 0. So from the left, this function approaches 3. From the right, it approaches 0. And it doesn't actually matter which one of these is an open circle or a closed circle. Remember, the limit doesn't depend on the actual function value. The function value is 0. But the limit doesn't depend on that function value. We could change that function value and still have the same limit. All right. Lastly, what's the limit as x approaches 2? What's the two-sided limit? Not from the left, not from the right. What is the limit here? Well, we learned that the limit exists. Look at that blue box. The limit exists if and only if the one-sided limits are the same. Well, look at these. Are these the same? No. They're not the same. So this limit does not exist. Let's just pretend that's a normal n. All right. And that's what we've got going on here. So that's kind of a connection between one-sided limits, limits from the left, limits from the right. Sometimes they won't equal. And so there is no two-sided limit. And sometimes, like in the sine of 1 over x case, where it's going, that's what the actual function sounds like. Neither limit, no limits exist at 0. Not the one-sided limit, not the other-sided limit. So those are some things that you can see here. Let me know if you have questions and have fun. I was gonna get excited and give you some other things to look at, but I want to keep you wanting more math. All right, don't want to give you too much. All right. Anyway, bye-bye.